previous lecture, you have learned the two types of transformations between frames, translation and rotation. Our ultimate objective is to find the relation between poses in two different frames that are translated and rotated between each other. We will first start by analyzing the translation, then the rotation, then the combination of both. Let's get started with translation. Consider the following two frames, W1 and W2, and the robot represented by the triangle. We clearly observe in this simple example that the location of the robot is 8,5 in W1 and 5,3 in W2. Let us analyze this further and find the general relation. We can observe that W2 is translated from W1 by 3 ticks in the x-axis and by 2 ticks on the y-axis. So we have a translation vector of 3 ticks in the x-axis and 2 ticks in the y-axis. We can say that the translation vector T is defined by x equal to 3 and y equal to 2 on the respective axis. It is clear that we can write that the x-coordinate of the robot in W1 is equal to the x-coordinate of the robot in W2 plus the 3 ticks. In the same way, the y-coordinate of the robot in W1 is equal to the y-coordinate of the robot in W2 plus the 2 ticks. So we obtain the following system of equations which determine the relation of the position of the robot in the two frames related by a translation. Using a matrix representation of the equation, we can write the equation system as a sum of vectors, where the vector xy in W1 is equal to the vector xy in W2 plus the translation vector 3, 2. Observe the translation vector represents the amount of translation between W1 and W2. This is the general relation between the poses in the two different frames related by a translation. Having understood how it works for translation, let us look at the relation between rotated frames in the next lecture. In the previous lecture, you have learned how to transform the pose of a robot from one frame to another frame related by a pure translation. In this lecture, you will learn how to do the same for a rotation between two frames. Let us consider a robot in the frame W1. The coordinate of the robot in W1 is 8,5 and 45 degrees of rotation angle. Now look at the frame W2, which is rotated by an angle theta with respect to W1. Our objective is to find the relation between the pose of the robot in W1 and its respective pose in W2, while W1 and W2 are rotated with respect to each other. I will take you step by step in demonstrating the relation between the poses. However, it's not a problem if you do not understand this demonstration, because what matters is the final general result, which is simple to use. And even better, in ROS, we do not have to deal with all this math, because ROS performs all the work for us and make all these transformations a piece of cake. Now the objective is to find the coordinate of x in W1, which is shown in the blue line. xW1 is equal to x in W2 multiplied by the cosine theta, which is the red line. Then we subtract the extra yellow line, which corresponds exactly to y in W2 multiplied by the sine of theta. As a consequence, we can obtain the following relation between x in W1 as a function of the coordinate in W2. We can do the same for y in W1, and we obtain a similar relation equal to the sine theta multiplied by x in W2 plus the cosine of theta multiplied by y in W2. This is again an equation system that we can write in a matrix form. Finally, we can write the relation between the poses in the two frames in the following matrix form. This means that x in W1 is equal to x in W2 multiplied by the cosine of theta minus y in W2 multiplied by the sine of theta. Also, y in W1 is equal to y in W2 multiplied by the sine of theta plus y in W2 multiplied by the cosine of theta. The matrix that converts the coordinate from W1 to W2 is called the rotation matrix and is dependent on the angle theta, as it can be observed. So now If we have x, y in W2, and we have a rotation matrix for the transformation between W1 to W2, then we can easily derive the coordinate xy in W1. It is as simple as that. So far, we have observed the case of a pure translation and the case of a pure rotation. What if we have a transformation that involves both a translation and a rotation? This is what we will discuss in the next lecture. In the previous lecture, we have presented the transformation matrix for a pure translation and the transformation of a pure rotation. However, in real world, transformations can be composed of translation plus rotation at the same time. In this lecture, we will present how to convert the coordinates between two frames with a general transformation. Remember that a 2D transformation involves one translation and one rotation. Observe in this slide the two frames W1 and W2. W2 is translated with respect to W1 by the translation vector t, with xt equal to 6 and yt equal to 2, which results in the translation vector with the blue color. In addition, we can observe that W2 is rotated by an angle theta with respect to W1. Thus, in this example, W2 is shifted from W1 by a translation of the vector t and a rotation of the angle theta. In the same way, we can determine a transformation matrix between the two frames that captures the translation and the rotation shifts. Here is the general expression of the 2D transformation matrix. The transformation matrix from W1 to W2 combines both the translation vector and the rotation matrix and is expressed as shown in this slide. First, observe that the location vector contains 3 values instead of 2 values, x, y. This is called the homogeneous coordinates, which is the traditional x and y coordinate values, and we add 1 at the end on both sides. This is to allow for writing the matrix representation that combines both rotation and translation. Without homogeneous coordinate representation, we cannot write this matrix form. So, x in W1 is equal to cos theta multiplied by x in W2 minus sin theta multiplied by y in W2 plus the additional xt that represents the translation in the y-axis. In the same way, y in W1 is equal to the sin theta multiplied by x in W2 plus cosine theta multiplied by y in W2 plus the additional yt that represents the translation in the y-axis. Note that this transformation matrix is for a counterclockwise rotation angle. For a clockwise rotation, the sign of the sin theta will be the opposite. That is all the story. Now, if we know the transformation between two frames and the coordinate in one frame, we can simply find the coordinate of the position in the other frame by using the transformation matrix. Let us apply this on an example to understand in the next lecture. In the previous lecture, you have learned how to transform location coordinates between two frames that are shifted by a translation and a rotation. But you may ask why this is useful and in which context we need it. In this lecture, I will present a simple example to show why transformations are very important indeed. Let us get started. Let us consider again our example of a robot that observes a person with its camera. Thus, the robot is able to determine the location of the person with respect to itself. Let us assume that the robot identified the position of the person to be 6, 3.5. 6 on the x-axis and 3.5 on the y-axis with respect to the frame attached to the robot. On the other hand, the robot is also navigating in its environment. Using some localization techniques, the robot is able to tell its location in the map of the environment with respect to a global reference frame. That is called the world frame. Let's assume that the robot finds that its position in the world is 3 in the x-axis and 3 in the y-axis of the global world frame. Now the question, what is the position of the person in the world frame? First, we need to determine the transformation matrix between the world frame and the robot frame. We can observe that we have one translation where xt is equal to 3 and yt is equal to 3, the translation vector between the word frame and the robot frame. We observe that there is no rotation, so the rotation angle is 0. Let us apply the transformation matrix formula by replacing the rotation angle theta by 0 and the xt by 3 and the yt by 3. By calculating the values, we can find the following numerical transformation matrix. We have 1, 0, 0 in the first column, 0, 1, 0 in the second column, and 3, 3, 1 in the third column. Now we apply matrix multiplication by multiplying every row of the matrix by the location vector of the person in the robot frame. So the x of the person in the word frame is equal 1 multiplied by 6 plus 0 multiplied by 3.5 plus 1 multiplied by 3. And in this case, we find xt in the word frame, or x of the person in the word frame is equal to 9. In the same way, the y of the person in the word frame is calculated as 6.5. If we verify in the figure, we can clearly observe that the value obtained by computation are correct and that the person is located at 9 on the x-axis and 6.5 on the y-axis in the word frame. Congratulations! You are now able to calculate the coordinate in 2 different frames using the transformation matrix in 2-dimensional space. In robotics applications, usually we consider 3D spaces. In the next lectures, we will show how to calculate the transformation matrix in 3D space. In the previous section, you have learned how to transform the coordinate of a position between two frames that are shifted by a translation and rotation in 2-dimensional space. However, in robotics applications, we typically use a 3-dimensional coordinate system which covers both ground robots and aerial robots like drones. In fact, in addition to the XY coordinates of a plane ground, we may also have an altitude z that indicates the height with respect to the ground. For example, a drone flies above the ground, so its altitude is greater than 0. For this reason, we need a general 3-dimensional coordinate system for all kinds of robots. Even for ground robots, like the red car in these slides, we use a 3-dimensional coordinate system, but we consider that the altitude z is always 0. In this section, you will learn how to represent a coordinate of a pose in a 3-dimensional space, and also how to transform between two 3-dimensional coordinate systems and the expression of the transformation matrix. In this lecture, you will learn about the right-hand rule. When dealing with a 3D coordinate system, we have 3 axes, x, y, and z. We have a 2-dimensional space defined by the xy axis, and the z-axis will be the orthogonal axis to this plane. Given a 2-dimensional plane xy, we have 2 options to place the z-axis, either looking upward or downward. The question is how to place the z-axis direction. One option is to have the z-axis pointing upward to the xy plane, like shown in this slide. A second option is to have the z-axis pointing downward of the xy plane. To resolve this tie, we need to follow the right-hand rule convention. It is a convention in robotics that specifies the direction of the three axes in a three-dimensional coordinate frame. Coordinates are usually right-handed. For right-handed coordinates, the right thumb points along the z-axis in the positive direction, and the curve of the fingers represent a motion from the x-axis to the y-axis. So, following the right-hand rule, z should be pointed downward in this example. When viewed from the top or the z-axis, the system is counterclockwise. This is a simple rule that you can follow as well. Typically, the x, y, and z unit vectors in a Cartesian coordinate system are chosen to follow the right-hand rule. Right-handed coordinate systems are often used in rigid body and kinematics, and more generally in robotics. Let us do some practice on the right-hand rule in the next lecture. In the previous lecture, you have learned about the right-hand rule. Let us make a small exercise to practice on it. Let us consider the following coordinate system. There are two possible options for the direction of the z-axis, either the blue line or the red line. What would be the correct z-axis direction according to the right-hand rule? Is it the blue line or the red line? Have some time to check with your right-hand fingers or just apply the counterclockwise rule. I give you 20 seconds to think about that. So the solution is that z must be looking downward, the blue line. In fact, looking from the top of z, the system is counterclockwise. If z was looking upwards, then the system will be clockwise. Thus, to make it the opposite, z has to be looking downward, and thus the system becomes counterclockwise when looking from the top of the z-axis that is looking downward.